All right, y'all. So we are going to talk about limits today. And let's go ahead and get started with the old definition of a limit. So this is one of the great things about mathematics is that it has been built on for hundreds and hundreds of years. So this is the first time the notion of a limit, which is like our first basic calculus concept, appeared. And it showed up in Euclid's Elements, which is a very old mathematics textbook, one of the first, as this two unequal magnitudes being set out. If from the greater there is subtracted a magnitude greater than its half, and from that which is left a magnitude greater than its half, and if this process is repeated continually, then there will be some magnitude less than the lesser magnitude set out. I have no idea what that means, and I've spent my whole life studying mathematics. That is clunky, it is awkward, and there is no notation there. So very, very difficult to work with. So fortunately, the limit and calculus in general was actually developed fully by Bernard Bolzano in 1817. Now, a lot of credit is also due to Isaac Newton and Leibniz, who kind of created a lot of the calculus that was then later developed by Bolzano. So the calculus that we actually use now is worlds apart from what Newton and Leibniz both created even before that. Now, most of the modern notation that we use, and we'll see in the slides to come, those were actually developed by G.H. Hardy in the early 1900s. And you can see a lot of the original kind of calculus, like the OG calculus textbook, would be his publication, A Course of Pure Mathematics. This gives most of the definitions and theorems and techniques that we still use today in modern calculus. So Bolzano himself was a religion and philosophy professor at Prague University. He kind of had his hands in a lot of different pots. He published papers over a wide range of fields, including mathematics. And he did most of his work in mathematics after he was exiled and fired shortly after making professor due to his political beliefs. And after that, he was also banned from publishing anything in any academic publication. So he retired to the countryside and did most of his work just kind of in his spare time. He created the first analytic proof of the fundamental theorem of algebra, which guarantees the existence of a root of a polynomial. And he also conceptualized the usage of epsilon delta limits, which are still used today in the field of real analysis, otherwise known as Calc 4 or ACAL. So a lot of this stuff that was done a couple hundred years ago is still commonplace today. So some very big ideas were being developed. So we'll start off with this graph of the position of a car as it travels with the position recorded every second. So when you are in a car, that speedometer that's attached to your car gives you what you would think is the instantaneous speed of your car. So your car speed at any given instant. Now, if you were to take just a freeze frame of time, you wouldn't be able to really detect motion at all because, well, what is motion? Motion is how much something changes in position versus the time that it takes to do so. So if you got in your car and you had to wait an hour before you could figure out your miles per hour, that wouldn't really be very accurate, and it wouldn't really be very helpful information to have to wait an hour every single time that you'd like to know your car's speed in miles per hour. So what your car does is it actually breaks down your speed into the revolutions that a wheel makes per fraction of a second. I'm not exactly sure how much. So what we have here is the car's position versus time. And what we're going to do is we're going to call this function here. Let's give it a name. Let's call it P of t. So the position of the car as a function of time. So if I wanted to know the car's position at, say, 4, we could plug 4 in. And since we don't have a function, we'd have to go up and look at our graph. So here's t equals 4. And at 4 seconds, our car's position would be at what appears to be about, let's say, 35. So we have a graph, so everything's not going to be, 100% accurate. It is going to be a bit of an approximation anyway. So if I wanted to know the car's average speed on this time interval, what we're going to do is we're just going to make a line connecting where the car is at 0 and where the car is at 10. This is very similar to, if you're driving somewhere that's 70 miles away and it takes you 1 hour to do so. You're dividing the distance you travel, 70, by the number of hours that it takes to travel, which is 1. So what we want to do is figure out the car's position at 10 and the car's position at 0 and take the difference of those two things. So that would be P of 10 minus P of 0. And then we want to divide by the total time that we have. So we have 10, and then we're starting at 0, so we would have 10 minus 0. This is very, very similar to another formula that we have used quite a bit in college algebra. And that formula would be just our basic formula for slope. So remember, for slope is y2 minus y1 over x2 minus x1. And what are these values that we've got over here? These are y values up here. P of 10 is referring to this value that's right up here. P of 0 is referring to the y value, or the position of the car at 0. And then we're dividing by x2, which is 10, minus x1. So the difference in the car's position divided by the difference in time. Okay, so at 10, it looks like we're probably at 58, it looks like. And then at 0, our car's position is at 0. So we have 58 minus 0 over 10 minus 0, which works out to be 5.8, and that would be meters per second. We have meters in the top, and then we have seconds in the denominator, so meters per second. Now, this average speed that we've calculated, or it's more commonly called an average rate of change, it's not accurate for every different instance of our car's travel. So like right here, for instance, our car is at a dead stop. We're at 40 meters at 5 seconds, and then we're also at 40 meters at 6 seconds. So our car stops traveling forward or backwards or anywhere on that time interval. So if we were to say that the speed were 5.8 meters per second everywhere, that wouldn't be a very accurate thing to say. Our car's average speed is 5.8 meters per second. But remember, that's an average. So there were probably instances where we were traveling above that speed, some instances where we're traveling below that speed, etc. So let's get the car's average speed from seconds 4 to 6. So on our graph, we're right here at 4, and then we're right over there at 6. So what we're going to do is take the difference of the car's position in the top. So we have P of 6 minus P of 4 over 6 minus 4. So at 6, our car is at 40 meters. At 4, our car is right here at, looks like 35 meters. And then 6 minus 4 is equal to 2. So our car would be traveling at an average speed of 2.5 or 5/2 meters per second from t equals 4 to t equals 6. Now this last question that's on here, which is, what about the car's speed at 6.4 seconds? So that's a little bit trickier. If you look on our graph, we really don't have that much information about our car's speed. We just have a little snapshot, so at every second we know where our car is, but we don't really know where our car is exactly in between those seconds. So we're just kind of connecting the dots between the information that we know. So the best that we can do to get what's called an instantaneous speed when we don't have the function itself is we can get an estimate by taking the car's average speed near 6.4 seconds. So let's do that. So 6.4 is in between 6 and 7, which is right there. So if we calculate the average rate of change between 6 and 7, it'll give us a pretty good idea of what our car's speed would be at 6.4 seconds, but still not really that exact, but let's do that. So P of 7 minus P of 6 divided by 7 minus 6. So at 7, looks like we're at 55. And then at 6, we're at 40. So our average rate of speed at 6.4 seconds, we could estimate as 15 meters per second. So even though our average speed over the time interval is 5.8, if we look at it between 6 and 7, it's 3 times that. And then if we look at it between 4 and 6, it's half of that. So our speed is fluctuating as we travel quite a bit. So the smaller and smaller time interval we use, the more accurate we can be.